of real line and constructive reverse mathematics. Very, very happy to have you in our group in Sendai, and your wife. And will you be happy to be interrupted in between for small questions?
Yes.
Yeah. Okay. So if you have some small clarificatory questions, you can ask. Don't ask the most difficult, steep, challenging questions. Keep them towards the end. Yeah? Okay, so all yours.
Okay, good evening everyone. Here I'm going to talk about the decomposability of R and dense negative subsets of R in constructive reverse mathematics. This is actually the title of our submitted paper, which I collaborated with Professor Mohammad Ardeshir, who is my supervisor at the Department of Mathematical Sciences at Sharif University of Technology. As you can see, this work is a contribution to the program of constructive reverse mathematics. So before anything, we should give a brief introduction to the topic. I'm sure many of you are familiar with the topic, but it's not a bad idea to remind some important definitions and facts and ideas in the program. So we start with an introduction to constructive reverse mathematics. First of all, I want to introduce Bishop's constructive mathematics. It's an informal mathematics using intuitionistic logic and assuming some function existence axioms. By intuitionistic logic, we mean the classical logic without the law of the excluded middle. And by function existence axioms, we mean these three axioms: the axiom of countable choice, the axiom of dependent choice, and the axiom of unique choice. Of course, there are some constructive justifications for these axioms, but still there are some constructive mathematicians who don't believe in these choice axioms, but at least in Bishop's constructive mathematics, there is no problem to use these axioms to prove theorems. Now you can see some famous extensions of Bishop's constructive mathematics: classical mathematics, intuitionistic mathematics, and Russian constructive mathematics. If you add the law of the excluded middle to Bishop's constructive mathematics, you get classical mathematics. If you add the continuity principle and Fan theorem to Bishop's constructive mathematics, you get intuitionistic mathematics. And if you add Markov's principle and Church's thesis to Bishop's constructive mathematics, you get Russian constructive mathematics. Therefore, if we prove a theorem in Bishop's constructive mathematics, it also would be a theorem in classical, intuitionistic, and Russian constructive mathematics. But of course, there are some theorems, for example, in classical mathematics, that cannot be proved in Bishop's constructive mathematics. And even worse, its negation can be proved in intuitionistic mathematics or in Russian constructive mathematics. So there are varieties of theorems here, and we may see some theorems and some examples in the next slides. And the question is, what is constructive reverse mathematics? The main question of constructive reverse mathematics is that given a theorem T in one of these three mathematics, T can be a theorem in classical mathematics, intuitionistic mathematics, or Russian mathematics. For example, T can be the intermediate value theorem in classical mathematics, or T can be a famous theorem of Brouwer, every real function is continuous, in intuitionistic mathematics, or T can be a theorem in Russian constructive mathematics. For example, there exists a Specker sequence, a sequence which is bounded above and monotone but doesn't converge to any real number. T can be any theorem in one of these three mathematics. Then the question is, can we prove T in Bishop's constructive mathematics? If we can, then there is no other question here. But if we cannot, there is one important question, which is the main question of constructive reverse mathematics. Which axiom is essential to prove that theorem? By the word essential, we mean both sufficient and necessary to prove that theorem. In other words, we are looking for an axiom which is equivalent to that theorem over Bishop's constructive mathematics. If you pick a theorem in one of these mathematics and you find an equivalent axiom for that theorem, then that would be a good introduction to the program of constructive reverse mathematics. So this is the main question of the program. Therefore, for every theorem in mathematics, there is a question of constructive reverse mathematics. Which axiom is equivalent to that theorem over Bishop's constructive mathematics? Okay? The next question I should answer is that what are the axioms? What are the axioms that we should be looking for? Of course, there are a lot of famous and important axioms in the literature of constructive reverse mathematics, but I'm not going to talk about all of them. But I'm going to talk about some of them that are somehow relevant to our discussion. And here you can see a list of important axioms in the literature of constructive reverse mathematics. The first one is the law of the excluded middle, which states that for all proposition P, either P holds or the negation of P holds. It's a very famous principle. The other axiom, which is weaker than the law of the excluded middle, is the limited principle of omniscience, which is actually an instance of the law of the excluded middle. In fact, it's the law of the excluded middle for binary sequences. It says that for all binary sequence AN, either there exists n such that AN equals 1, or it's not the case that there exists n such that AN equals 1. Another weaker axiom that the limited principle of omniscience is the weak limited principle of omniscience, which is again an instance of the law of the excluded middle. And you can get the weak limited principle of omniscience by replacing this sentence by not that sentence. And these two are not equivalent in constructive mathematics because we don't have the law of double negation elimination. Because we don't have the law of the excluded middle, we lose double negation elimination. So these two are different, and actually WLPO is weaker than LPO. Another weaker axiom than WLPO is LLPO, a lesser limited principle of omniscience, which is actually an instance of the Morgan's law for binary sequences. It states that if AN is a binary sequence with at most 1, 1, then either all even terms are 0 or all odd terms are 0. Obviously, it is a true statement in classical mathematics, but it cannot be proved in Bishop's constructive mathematics. In fact, none of these theorems can be proved in Bishop's constructive mathematics. And another weaker axiom than LLPO is WLLPO, or it's also known as the disjunctive version of Markov's principle. It has two names because you can get this axiom by weakening LLPO, or you can get this axiom by weakening Markov's principle. If you get this axiom by weakening LLPO, then its name would be WLLPO, and if you get this axiom by weakening Markov's principle, then its name would be disjunctive version of Markov's principle. And it says that if AN is a binary sequence with at most 1, 1, and this is the difference between WLLPO and LLPO, and it's not the case that all terms are 0, then either all odd terms are 0, or even terms are 0, or all odd terms are 0. This is exactly the conclusion that you can see in the conclusion of LLPO. So obviously WLLPO is weaker than LLPO. Here, these are some important and famous axioms in constructive reverse mathematics. We can also negate these axioms and achieve some other axioms. For example, the negation of LPO is also an axiom in constructive reverse mathematics, or the negation of WLPO, or negation of LLPO, and for all of them. If you negate them, then you can get an axiom in constructive reverse mathematics. Of course, the negation of LPO is not true in classical mathematics, but it is true in intuitionistic mathematics, or in Russian constructive mathematics. So we have more than these axioms here, actually. Now you can see, and I'm going to introduce you some important contributions to the program of constructive reverse mathematics. I've taken most of these examples from the paper Reverse Mathematics in Bishop's Constructive Mathematics, written by Professor Ishihara, which is a very good introduction to the topic of constructive reverse mathematics. And here you can see some contributions. This is a list of equivalent theorems to LPO. All of these theorems are equivalent to LPO. Analytic LPO, which states that for all real number x, if x is a real number, then either x is less than 0 or not, which is an instance of the law of the excluded middle for real numbers. This is why it's called analytic LPO. These two are actually equivalent. Analytic LPO is equivalent to LPO. The monotone convergence theorem, which is a very famous theorem in mathematical analysis, the Bolzano-Weierstrass theorem, the sequential compactness theorem, and the Seodo-Heine-Borel theorem, all of them are equivalent to LPO. This is a very interesting picture of constructive reverse mathematics. You can see all of these theorems are equivalent to each other and equivalent to LPO over Bishop's constructive mathematics. We can also see the name of mathematician who actually proved the equivalence in the blue color. Here you can see a list of equivalent theorems to WLPO. All of them are equivalent to WLPO. Analytic WLPO, which states that for all real number x, if x is a real number, then either not x is less than 0 or not x is less than 0, which is again an instance of the law of the excluded middle, but it's obviously weaker than LP. It's weaker than LPO. And also the decidability of equality for real numbers. It's again equivalent to WLPO. For all real number, for all x in R, either x is 0 or it's not the case that x is 0. It's equivalent to WLPO. So we cannot prove in Bishop's constructive mathematics then that the equality for real numbers is decidable. If we want to prove that, we need the axiom WLPO. The other theorem which is equivalent to WLPO is the existence of a discontinuous function. If you want to prove that there exists a discontinuous function, it's actually equivalent to WLPO. And also the existence of a bijection from this interval to this interval is also equivalent to WLPO. And we want to add one more to this list. We can see the theorem in the next slides. Here you can see a list of the negation of WLPO. The negation of WLPO is equivalent to the non-discontinuity theorem, which states that every mapping from a complete metric space to a metric space is non-discontinuous, which implies that every real function is non-discontinuous. Obviously, it's not a classical theorem, because in classical mathematics we have discontinuous functions. But here we can prove that in intuitionistic mathematics we can prove that the non-discontinuity theorem, and it's actually equivalent to the negation of WLPO. And also the indecomposability of R is equivalent to the negation of WLPO. And we are going to talk about this theorem in the next slide. Here you can see some important theorems that are equivalent to LLPO. Analytic LLPO, which just states that for all x in R, either it's not the case that x is less than 0, or it's not the case that x is greater than 0. And Koenig lemma, the intermediate value theorem, the minimum principle, all of these theorems are equivalent to LLPO. So this is what constructive reverse mathematics is about. It's actually measuring theorems. How is the strength of a specific theorem? It's about classifying various theorems in mathematics into one simple axiom. For example, you can see here that the existence of a bijection from this interval to this interval is strictly stronger than the minimum principle, for example, because WLPO is strictly stronger than LLPO. Okay, here you can see a list of equivalent theorems to WLLPO, which is also known as disjunctive version of Markov's principle. Analytic WLLPO, it changed a little bit in this PowerPoint, sorry. It means for all x in R minus 0, either it's not the case that x is less than 0, or it's not the case that x is greater than 0. And we want to also add one more to this list. And here you can see some important theorems that are equivalent to the negation of WLLPO, the indecomposability of R minus 0, and we want to also add one more to this list. Okay, the introduction is over. Now you saw some important contributions to the program of constructive reverse mathematics, and you're now familiar with the main question of constructive reverse mathematics. Now I'm going to talk about our contribution, and I start with the definition of the notion of decomposability. The definition is this. We say that the set X is decomposable and denoted by decom of X if there exist two inhabited disjoint subsets A and B such that X equals A union B. By inhabitedness, we mean there exists an element of that set. There exists A in capital A. It means that A is inhabited. It implies that A is not empty. And in classical mathematics, we also have the other direction. But in constructive mathematics, the other direction is not always true. Inhabitedness is actually stronger than non-emptiness. So here, the assumption is inhabitedness. The two sets A and B must be inhabited. And disjoint means that the intersection equals empty set. And X must be equal to A union B. This is the definition of the decomposability of a set X. For example, the set of natural numbers n can be decomposed into these two sets, the singleton 0 and the set of all natural numbers which are non-zero. Because we have the decidability of equality in natural numbers, even in constructive mathematics. Also, we can prove that the set of integers is decomposable, and the set of rationals is decomposable in Bishop's constructive mathematics. So in classical mathematics, intuitionistic mathematics, and Russian mathematics, the set of natural numbers, integers, and rationals are decomposable because they are decomposable in Bishop's constructive mathematics. And a very interesting and important and trivial fact is that the classical continuum is decomposable thanks to the law of the excluded middle. In classical mathematics, we can write and we can decompose R into these two sets, Q union QC, because for all x in R, either x is rational or not. This is an instance of the law of the excluded middle. And also we can decompose R into these two sets, for example. But the thing is, all of these examples are using the law of the excluded middle. So the question is, can we prove that R, the set of real numbers R, is decomposable in Bishop's constructive mathematics or not? We will come back to this question later. Now I'm going to introduce you the notion of indecomposability. The definition is this. A set X is said to be indecomposable, denoted by indecom of X, whenever for all disjoint subsets A and B, if X equals A union B, then either X equals A or X equals B. This is the meaning of indecomposability. And as you may already notice, the relation between the indecomposability and decomposability is this. The indecomposability of X is exactly equivalent to the negation of the decomposability of X. The proof is straightforward, you can see that. And the notion of indecomposability has investigated by Brouwer, Van Dalen, Troelstra, and Loeb. Maybe another mathematicians, but as far as I know, these four mathematicians did a lot of researches concerning the notion of indecomposability. The story began with the famous theorem of Brouwer, who proved that the intuitionistic continuum is indecomposable. It's a very interesting theorem. The theorem is this. In intuitionistic mathematics, the set of real numbers R is indecomposable, which means R cannot be decomposed into any two sets in intuitionistic mathematics. I've taken this proof by the book Constructivism in Mathematics, written by Troelstra and Van Dalen, and the proof is very simple. In intuitionistic mathematics, every real function is continuous. It is a very famous theorem of Brouwer. So now suppose A and B are disjoint and R equals A union B. Now define the function f from real numbers to integers by this statement. Remember, R equals A union B means that for all real number x, we can decide whether x is in A or x is in B. So we can define this function. If x is in A, then f of x is 0, and if x is in B, then f of x is 1. The function f must be constant because f is both continuous and from reals to naturals. We can prove that f must be constant. Therefore, either for all x in real numbers, f of x is 1, or for all x in R, f of x is 0. If for all x in R, f of x is 1, then R equals B, and if for all x, f of x is 0, then then R equals A, which means R is indecomposable. This is the proof of the indecomposability of the continuum. So the answer to our question is no, is negative. Can we prove the decomposability of R in Bishop's constructive mathematics? No, because the set of real numbers R is not decomposable in intuitionistic mathematics. If we can prove the decomposability of R in Bishop's constructive mathematics, it must be also decomposable in intuitionistic mathematics. But we saw that this is not the case. So we cannot prove the decomposability of R in Bishop's constructive mathematics. Okay, now we have two theorems. One is the decomposability of R in classical mathematics, and the other is the indecomposability of R in intuitionistic mathematics. So the reverse mathematical question here is that which axiom is equivalent to the decomposability of R, and which axiom is equivalent to the indecomposability of R? You can see these two questions here. Which axiom is equivalent to indecomposability of R? Answered by Loeb at 2008. Which axiom is equivalent to the decomposability of R? Answered in our paper at 225. You can see the answers here. The indecomposability of R is equivalent to the negation of WLPO. It is proved by Loeb. And the decomposability of R is equivalent to WLPO. Actually, we saw the result of Loeb, and we were aware of that the indecomposability of R is equivalent to the negation of the decomposability of R. And since the negation of the decomposability of R is equivalent to the negation of WLPO, we expected that it must be true that decomposability of R is equivalent to WLPO. It's not always true in constructive mathematics, but here it was the case, and we proved it. Actually, in classical mathematics, if the negation of A is equivalent to the negation of B, you can immediately conclude that A is equivalent to B. This is obvious in classical mathematics, but in constructive mathematics, this is actually strictly stronger than this. We cannot prove the other direction here. But here, it was the case actually. The decomposability of R is equivalent to WLPO. We actually added something to this list. Remember the list of WLPO? It was equivalent to the decidability of equality. It's equivalent to the existence of a discontinuous function. It's equivalent to the existence of a bijection from this interval to this interval. And it's equivalent to the decomposability of R. It reveals some hidden facts about the nature of the continuum. You can see the relations here. The decomposability of R, if you can decompose R into two sets, then there exists a discontinuous function. Then there exists a bijection from this interval to this interval. This is a good thing to think about, especially for those who are interested in philosophy of mathematics and philosophy of continuum. Okay, we can see this result from a different perspective here. What does it mean when we say that the decomposability of R is equivalent to WLPO? Let me remind you the definition of analytic WLPO. It says that R can be decomposed into these two sets, singleton zero and the set of all real numbers which are non-zero. It means equality is decidable. Okay? And the decomposability of R says that there exist two sets that decompose R. We don't know anything about those two sets. We just know that those two sets decompose R. And the decomposability of R being equivalent to the WLPO means if R is decomposed by any two sets, it can also be decomposed by A and B, this A and B. Which means equality is the weakest non-trivial property of real numbers with respect to decidability. If there exists a property P such that P is decidable and non-trivial, if there exists a property P with these conditions, any property with these conditions, if there exists a property P with these conditions, then equality is one of those properties. Actually, equality is the weakest non-trivial property concerning decidability. Okay? I've also written the proof, but if we have time, we can get back to these slides again and read the proof. Okay, the problem of the decomposability and the indecomposability of R has been resolved. As far as the Bishop's constructive reverse mathematics concerned, there is no other questions here. But what about R minus 0? This means minus. R minus 0 and R minus Q. Are they also indecomposable in intuitionistic mathematics? Of course, R minus 0 is decomposable in classical mathematics, thanks to the law of the excluded middle. Okay? But are they also indecomposable in intuitionistic mathematics or not? The answer is yes. In the paper, How Connected is the Intuitionistic Continuum, Van Dalen has proved that assuming these principles, we can prove the indecomposability of R minus 0 and the indecomposability of R minus Q. So in intuitionistic mathematics, R minus 0, and R minus Q, all of them are indecomposable. At the end of that paper, Van Dalen asks which other principles imply the indecomposability of R minus Q. Van Dalen actually was curious about this question. Let's forget about this question for a moment and think about these theorems in a reverse mathematical manner. We have 4 theorems here. First, the decomposability of R minus 0. The decomposability of R minus 0 in classical mathematics. The indecomposability of R minus 0 in intuitionistic mathematics. And the indecomposability of R minus Q in intuitionistic mathematics. And the decomposability of R minus Q in classical mathematics. So we have 4 questions concerning constructive reverse mathematics. Which axiom is equivalent to indecomposability of R minus 0? And the same question for the decomposability of R minus 0. Same question for the indecomposability of R minus Q and the decomposability of R minus Q. We can see here the answers. The indecomposability of R minus 0 is equivalent to the negation of WLLPO, or it's also known as the negation of disjunctive version of Markov's principle. We could prove that the decomposability of R minus 0 is equivalent to WLLPO. Again, we saw the result of Loeb. We were aware of that the indecomposability of R minus 0 is exactly equivalent to the negation of the decomposability of R minus 0. And since the negation of the decomposability of R minus 0 is equivalent to the negation of WLLPO, we expected that the decomposability of R minus 0 must be equivalent to WLLPO. It's not always true in constructive mathematics, but actually it was the case, and we could prove it. What about R minus Q? The indecomposability of R minus Q is equivalent to a weakened version of Wesley's substitute, which is an axiom in the literature. I'm not going to talk about this axiom. But we proved that the decomposability of R minus Q is equivalent, again, to WLLPO. It is a very interesting fact. There is no difference between the decomposability of R minus 0 and the decomposability of R minus Q. There is a major difference between the decomposability of R and the decomposability of R minus 0. The decomposability of R is equivalent to WLPO. But the decomposability of R minus 0 is equivalent to WLLPO, which is very weaker than WLPO. Therefore, the decomposability of R minus 0 is very weaker than the decomposability of R. But there is no difference between the decomposability of R minus 0 and the decomposability of R minus Q. Both of them are equivalent to WLLPO. In other words, if you take out one point from the continuum, or if you take out countably infinite points from the continuum, that would make any differences concerning the decomposability. The decomposability of both of them are equivalent to WLPO. It's a very interesting fact about the continuum. We leave it to the philosophers of mathematics and the people who are very interested in philosophy of mathematics. It's a very good thing to think about. And we actually resolve the problem of the decomposability of R minus 0 and R minus Q and R in Bishop's constructive mathematics. There is no other questions here, but one can ask, what about the decomposability of R minus G? What about the decomposability of this set, where G is the set of all, for example, algebraic numbers? One can ask that question. What about the decomposability of this set? Or another one can ask about the decomposability of R minus E, where E is a set with some properties. These questions motivate us to actually motivate the mathematicians to think about this question in the most general form and solve the problem once and for all. This is why they define the negativity and density, and they try to consider the decomposability and indecomposability of dense negative subsets of the continuum. Here is the definition of negativity. We say that a set D is negative when for all x in R, not x is in D implies x is in D, which is obviously true in classical mathematics, but in constructive mathematics, it's not always true. The definition of density is well known for all x and y in R. If x is less than y, then there exists z in D such that z is greater than x and less than y. This is the definition of density for a set, for a subset D. Concrete examples here are R minus 0 and R minus Q. Both of them are dense and negative. Okay, you can see here 4 answers. The other answer is not shown here. We can see 3 answers here to Van Dolen's question. Remember Van Dolen's question? He asked about the indecomposability of R minus Q. Which principles imply the indecomposability of R minus Q? The first answer is the answer of Van Dolen himself. He proved that Kripke's schema implies the indecomposability of D, and he proved that, and Troelstra proved that Fan theorem and the independence of Permis implies the indecomposability of D, where D is a dense negative subset of real numbers. For example, R minus 0 or R minus Q. D is an arbitrary dense negative subset of continuum. And Loeb proved that the indecomposability of D is equivalent to a weakened version of Wesley's substitute, which is an axiom in the literature. And also the indecomposability of D is equivalent to the conjunction of these three principles. This is also a contribution to the program of constructive reverse mathematics because she actually found the equivalent axiom. Because she could prove the equivalence, then it is a good contribution to the program. And our answer is not shown on the screen. If I write it here. We could prove that over Bishop's constructive mathematics, the indecomposability of D is equivalent to W to the negation of WLLPO. It's our answer to Van Dolen's question. He asked about which principle implies the indecomposability of D, and we actually found the equivalent axiom. The negation of WLLPO is equivalent to the indecomposability of D. D is an arbitrary dense negative subset of real line. For example, R minus 0, R minus Q, R minus G, or any other dense negative subset. The indecomposability of all of them is equivalent to the negation of WLLPO. We actually proved a stronger theorem. We could prove that over BISH, the decomposability of D is equivalent to WLLPO, which immediately implies that the indecomposability of D is equivalent to the negation of WLLPO. We actually added something to this list. Over Bishop's constructive mathematics, the following are equivalent. Remember the list of WLLPO. It's equivalent to analytic WLLPO. It's equivalent to this statement for all x and y in R with not x is less than y. Then the set x and y is closed subset of R. And the decomposability of D, which is where D is a dense negative subset of R. All of them are equivalent. All of them are equivalent to WLLPO. And we also added something to this list because the decomposability of D being equivalent to WLLPO means the indecomposability of D is equivalent to the negation of WLLPO, because the indecomposability of D is exactly the negation of the decomposability of D. This is actually one answer to Van Dolen's question, because we found the equivalent axiom to indecomposability of D. And when you combine our work with Loeb's result, you can add another thing to this list. A weakened version of Wesley's substitute is also equivalent to the negation of WLLPO. And conjunction of these three principles also equivalent to the negation of WLLPO. Because she proved that a weakened version of Wesley's substitute is equivalent to the negation of WLLPO. We proved that the negation of WLLPO is equivalent to the indecomposability of D. And you can see the equivalences here. All of them are equivalent to each other. We also can see this result from a different perspective. What does it mean when we say that the decomposability of R minus 0, for example, an instance of a dense negative subset of R, is equivalent to WLLPO? Let me remind you what is analytic WLLPO. It says that R minus 0 can be decomposed into these two sets, or all real numbers x such that x is not less than 0, and all real numbers x such that x is not greater than 0. We can decompose R minus 0 into these two sets. decomposability of R minus 0 says that there exist two sets that decompose R minus 0. We don't know anything about those two sets. We just know that those two sets decompose R minus 0. Decomposability of R minus 0 being equivalent to WLLPO means if R minus 0 is decomposed by any two sets, it can also be decomposed by A and B. This is another perspective. This is another interpretation of this result. I've also written the proof. If I have time, I can get back to this slides again. So what have we done in summary? We have shown that the decomposability of R is equivalent to WLPO, and the decomposability of D is equivalent to WLLPO, where D is a dense negative subset of the continuum. For example, R minus 0, R minus Q, etc. Which implies the indecomposability of R is equivalent to the negation of WLPO, which is already proved by Law, and also implies that the indecomposability of D is equivalent to the negation of WLLPO. We also could replace the axiom of dependent choice with the axiom of countable choice in our proof. For the proof of the equivalence between WLLPO and the decomposability of D, we made use of the axiom of dependent choice at first. Just like Van Dalen, when he tried to prove Kripke's schema implies the indecomposability of D, he also made use of the axiom of dependent choice. But after that, we could avoid the axiom of dependent choice and replace it with axiom of countable choice, which is a weaker axiom. And the axiom of dependent choice is not essential for proving this equivalence, but the axiom of countable choice is enough. And I've also written the idea of the proof, but since we didn't see the proofs, maybe I omit it. There are some open questions here, some interesting open questions. First question is this: what happens if we don't use any kind of choice principles? In Bishop's constructive mathematics, we are allowed to use countable choice, dependent choice, and unique choice. What about if we don't want to use any choice principles? There are a lot of difficulties here. The first is that if we don't want to use any kind of choice principles, then the Cauchy real numbers and Dedekind real numbers are no longer isomorphic. And even worse, there are at least 7 non-isomorphic definitions of real numbers if we don't want to use the axiom of choice, any form of axiom of choice. So when we say that we want to investigate the decomposability of R, we have to specify which R are we talking about. Because we have 7 non-isomorphic real numbers, and this is a very difficult situation. The other difficulty is that when we don't want to use any kind of choice principles, then the analytic and sequential version of Omniscience principles are no longer equivalent. LPO is not equivalent to analytic LPO anymore if we don't want to use choice principles, because for proving the equivalence we have to use some choice principle. The second question is that can we formalize these results in an established formal system? Because as you saw, the Bishop's constructive mathematics is an informal mathematics. The question is, can we formalize these results in some formal system? For example, elementary analysis or its subsystems, or HA omega or its subsystems, etc. Well, we would like to thank Karl Mammert Robert Lobarsky, and especially Mohsen Shahriari for their insightful comments and suggestions. And also thank you for listening. If you have any questions, please feel free to ask. Thank you.
Great, fantastic. So who has some questions, comments, complaints, your insights, answers to open questions?
So if you know something about it, like a virus decrease or those computability related point of view for the constructive math, can you say something about the relation?
Say something about, can you clarify this for me?
So the if you know about the like virus decrease or those other like the computability related re-understanding of the constructive results, then maybe there's some connection. If you know something about it, that's really.
I don't understand you very well.
Okay.
Question. Do you understand?
You mean the computability theory?
Compatibility theory?
Computability theory.
Computability theory.
Yeah,
Yes.
theory, yeah.
It's the computability theory is somehow related to Russian constructive mathematics.
Sure, yes.
And in Russian constructive mathematics, we have some results about the decomposability and indecomposability that I didn't mention in my talk. If you're interested in Russian constructive mathematics, the set of real numbers R is also indecomposable again, and the set of R real numbers minus 0, R minus 0, is not indecomposable. It's actually decomposable. Continuum is indecomposable, but R minus 0, when you take out 1 point, it would be decomposable, and R minus Q is decomposable. And we can interpret the real numbers in Russian constructive mathematics as computable real numbers in some sense. Yes.
Okay, thank you.
Thank you.
I think his question is related to work by Vasco Bratka and his group.
Yeah, for example. Yeah.
And they are investigating so-called Omniscience principle, LPO, LLPO, from computable point of view.
Oh.
They also have a big list of
Yes.
principles.
Yes.
So maybe once you should look into
Yes. That's a
their
good.
result.
Yeah, that's a good idea.
Yes, okay, but this is already very informative, even from the viewpoint of computability, I can. So,
Yes.
yeah, thank you very much.
Yes, thank you. Thank you for your question.
Good. Other questions or comments? Everyone's convinced?
Okay, so could I ask?
Oh, yeah, of course.
So the if you think so here I guess they like R minus 0 or R minus Q, all those are more like provided by negative information, right?
Negative information, yes. They are both negative. So, yes.
So if you change the like definition of a difference of a set, then can we say some different then?
If we don't want to assume negativity?
Yeah,
you mean?
I mean, yes.
I think if we don't want to assume negativity, for example, we should think about some examples of subsets of real line which are not negative. For example, the set of rationals, rational numbers, it's decomposable. Even it's in Bishop's constructive mathematics, it's decomposable.
Yes.
And the set of irrational numbers, which can be defined in a positive way,
Right.
it's also, I think, it's also decomposable, I think. I'm not sure, but I guess it would be decomposable.
Okay, so then
And the
positive way
negativity
means,
is-
sorry.
Sorry?
Yeah, I guess the positive way means that it's more like a, how I would say, the irrational in the sense that the final expansion is, well, wait. So sorry, what's the definition of positive?
There are two different definitions actually. You can consider this set R minus Q, which I mentioned in my talk. I mean this set actually, all real numbers, which x is for all x in R, such that it's not the case that x is rational.
Yep.
Okay?
Yep.
It's a negative
Yes,
definition.
Yes,
But we can also define irrational numbers in constructive mathematics with some positive way. I don't remember the exact definition. Maybe some of you can help me here. But there is a definition of positive irrational numbers. They coincide in classical mathematics, but they are different. I can make an example here. For example, R minus 0 is the set of all real numbers which are not 0. Okay? Okay? But this is the definition of not being 0. But we have also another notation in the literature, this notation, which means that x is or less than 0, either less than 0 or greater than 0, which is strictly stronger than saying that x is not 0. This is positive, because when you say that x is less than 0, there exists a natural number n such that x plus 1 over n is less than 0. Actually, this is an existential statement. This is why it's positive.
I believe the positive way of defining irrational number is more or less using that title.
Yes, exactly.
Yeah.
The idea is the same.
Right. Yeah.
Yes, but I don't remember the exact definition here.
I think I can recover the definition.
Okay,
Yeah,
thank you. Thank you for your question. Any other question?
Any other questions? Okay, then thank you very much for your talk.
Thank you. Thank you for your question.
I think